Welcome to Unit 6, Geometric Vectors, Lesson 4, Word Problems for Vector Addition. Because we're going to do 4 examples here, and they're a bit lengthy examples, I'm going to split up example 1 and 2 in the first video, and the second video will contain examples 3 and 4. All the examples are a little bit different, so I also think it's another good reason to split the videos. So some key concepts before we continue with the examples. Rectangular vector components are two vectors that are perpendicular to each other and add to give another vector. Perpendicular is a really nice property because that means we can use Pythagorean theorem. Equilibrium vectors, the opposite of a resultant. Equilibrium vector is the opposite of the resultant vector, and it has equal magnitude as to the resultant but opposite direction, which of course means that the sum of the resultant and its equilibrium is always going to be the zero vector. Alright, so we'll see the rectangular vector component in example 1, and we'll see the equilibrium vector in example 2. So here's the first one. In a numeric model of the Bay of Fundy, which you can see a beautiful picture over here, you can see a much better picture in color on the website. The velocity of the water is given using rectangular vector components of 2.5 meters per second north 45 degrees west and 3.5 meters per second south 45 degrees west. Sketch the rectangular vector components and the resultant. Then calculate the magnitude and the direction of the resultant. So first of all, I'm going to sketch the rectangular vector components, and again, because it's rectangular vector components, I know the two vectors should be at 45 degrees. Here's the first one and the second one. So I'm going to sketch these first. I'm going to add them, and I'm going to draw the vector. I can see here that the second one has a bigger magnitude than the first one, so I'm going to draw this one's going to be a longer line segment than the first one. So here we go. I'll draw the first one, north 45 degrees west. So here we go. I'm going to draw my quadrant bearings. That's north. I'll draw my vector here. Not too long. So here's my first vector. There we go. Don't forget the tip, signified by an arrow. I know this is 45. And I know its magnitude is 2.5 meters per second. Alright, there we go. And then from there, I'm going to draw another quadrant bearing. So again, that's north. And now I'm in south, 45 degrees west. So I'm going to draw my second one here. A bit longer than my first one. There we go. I know this angle here is 45. By the way, using Z patterns, since this is 45, I know this is 45 as well, which signifies that this entire angle is 90, which of course bears with the fact that these are rectangular vector components. Alright. So I've got this. Now where's the resultant, Mr. Wills? The resultant starts at the tail of the first and goes to the tip of the second. I'm going to pull out my ruler again because I like to make sure my lines are drawn nice and straight. So here we go. So this is my resultant vector. This guy here. So that's what I want to find. So if we mark this one here is 3.5 meters per second. Alright, so my resultant is that vector r. I've got my two magnitudes, I've got a 90-degree angle here, so it's pretty easy to solve for the magnitude of that resultant. The magnitude of the resultant will be, since that is my hypotenuse, magnitude of r squared is equal to 2.5 squared plus 3.5 squared. Pull out my calculator. Try to put it somewhere over here. So here we go, 2.5 squared plus 3.5 squared gives me 18.5. And I can square root it again because I'm using a sharp calculator. It's very smart, so I know that my magnitude of the resultant is 4.3 meters per second. Alright, that was pretty straightforward. Now it wants it in the direction. So I want to find this angle here. Once I find this angle, what I really want is the direction of this. So I can see that this angle, I think, is in the southwest quadrant. But I'm going to find this angle here. I'll call this angle here theta. But what I really want is this angle here. I want that angle. It's called alpha. So let's find theta first. So I'm going to use sine law here. So sine of theta over 3.5 is equal to sine of 90. I could use SOHCAHTOA here. This is a bit ridiculous, but that's okay. Sine of 90 over my resultant 4.3. I'm a little embarrassed right now. So theta is equal to 3.5 sine of 90, which of course is just 1. Should be sine inverse of this whole thing. My apologies. Divided by 4.3. That's going to be sine inverse as I'm solving for an angle. So I'm going to put this in my calculator. Second embarrassment right there. Alright, 3.5 sine of 90. Mr. Rose, why do you put sine of 90? No, it's 1 divided by 4.3. So here I get an angle of 54.5. Now, what I really want is this alpha. But before I can find that alpha, I want to find this angle right here. That's a really tiny angle. Let's call that beta. Let's find that angle beta. Well, I know beta is actually equal to theta minus 45. How do you know that, Mr. Willis? Well, because if this angle here is 45, this angle here must also be 45. So if I can do theta minus 45, that'll give me angle beta. So beta is equal to 54.5 minus 45, which I believe is 9.5 degrees. Now what I really want is alpha. And I know alpha is equal to, since this right here, this between the south and west quadrant, that is 90 degrees. So alpha is equal to 90 minus my beta. So alpha is equal to 80.5 degrees. Why do I want it off of that vertical? Because again, I want to know direction. So now I know the direction of that resultant vector. So I know the magnitude is equal to 4.3 meters per second. The direction is going to be south 80.5 degrees west. And there we go. So I've got my direction and magnitude of that rectangular vector component. And that is example 1. Alright, let's go to example 2. Example 2 says this. A clown with a mass of 80 kilograms is shot out of a cannon with a horizontal force of 2,000 newtons. The vertical force is acceleration due to gravity, which is 9.8 meters per second downwards, times the mass of the clown. Determine the magnitude and direction of the resultant force of the clown. So, for part A, I'm going to draw a vector diagram. Shot out of a cannon at a horizontal force of 2,000. So here is my horizontal force of 2,000 newtons. There we go. Now, there is also a vertical force working here. The vertical force is the acceleration due to gravity. So the vertical force is acceleration due to gravity, which is 9.8 meters per second, times the mass of the clown. So I have to use this 80 kilograms. Alright, so when I do the vertical force, going down like this, it is going to be 9.8 times 80, which gives me 784 newtons. So my resultant vector, please excuse me while I use a ruler because I am not very good at drawing straight lines sometimes. So my resultant will be the tail of the first vector to the tip of the second vector, so that my resultant will be here. And so what I want is to determine the magnitude and direction of the resultant vector. So magnitude should not be a problem, because I can simply just do Pythagorean theorem. Thank you, Mr. Pythagoras, whoever came up with, or whoever came up with the first, which was probably not Pythagoras. In fact, historically speaking, it is not Pythagoras. 2000 squared plus 784 squared. So if I do this, I get a resultant of approximately 2,148.2 newtons. Excuse me for not showing the calculation, but I think you guys can all do that with your calculator. All right. Now, I also need the direction. So the direction will be this guy here. So I'm going to go using it. My direction will be clearly below the horizontal. So I want to know how many degrees below the horizontal will the direction be. So I can use this. Again, I know these two. Since that's horizontal and vertical, that's a 90-degree angle. So I can use SOHCAHTOA, which I should have used SOHCAHTOA at the first example, but my apologies. So I've got here, this is the opposite side. This is the adjacent side because my resultant is the hypotenuse. So opposite and adjacent, well, I'm going to use here tan. So tan theta is equal to opposite, which is 784 divided by 2000. So if I put this on my calculator, I get theta is equal to 21.4 degrees. And there we go. So right therefore statement therefore the resultant has a magnitude of 2,148.2 newtons, 21.4 degrees below the horizontal. There we go. Now, part B says this: determine the magnitude and direction of the equilibrium force. See below. So the equilibrium force is a vector that balances another vector or a combination of vectors. What does that mean? It is equal in magnitude but opposite in direction. Alright, so the equilibrium force. So what I want here is, I have to draw this out again very quickly. So again, I've got this guy here, I've got this guy here. My resultant, I'm going to do this with a ruler. Let's see if I can do a straight line with a ruler. Not bad, Mr. Wills. There's my resultant. So what I want is the equilibrium, which is actually going in the opposite direction. So what I want is this guy here, and I'll call that vector E. And I know vector R plus vector E is equal to the zero vector, since they are same magnitude but opposite direction. So what I need to do is find that direction. Now if I just continue my horizontal like this, again, I know this is 21.4 degrees, which means this is 21.4 degrees as well. So if I know that angle there is 21.4 degrees, I can figure out this angle is here. So that would be 180 minus 21.4 degrees, which would give me 158.6 degrees. So I can now write a therefore statement. Now, Mr. Wills, what's the magnitude of this green vector here, the equilibrium vector? Well, it's got to be the same as the resultant, right? Because it has equal magnitude but opposite direction. So I can write therefore. Therefore, the equilibrium force, right here, or vector, has a magnitude of 2,148.2 newtons in the direction of 158.6 degrees above the horizontal. So again, counterclockwise to the horizontal. I shouldn't say again, but that would be counterclockwise to the horizontal. Counterclockwise. So that is the end of example 2. Example 3 and 4 again can be watched in the next video.